Seems like we have a day of sunshine for once, and guess it's gonna start raining again on the weekend.
You will miss it. A few years from now, you will all miss it.
I don't know.
Oh my God, it's been 20 years for something like this.
My garage door doesn't work anymore, so it's kind of funny.
I know, we're so not prepared.
Yeah,
I have 2 umbrellas at home and one is broken. And I always discover it when it actually starts raining. So
I didn't
in
even own
LA,
one until last week.
of course, you don't have one.
Great, so today we are talking about kernel machines and in particular support vector machines. We're going to talk about like the main characteristics of them and like we'll identify the usefulness of them and like how they are actually quite different from what we've talked about so far. Alright, so kernel machines and use that thing. So kernel machines are often also just referred to as support vector machines, and I'm gonna probably interchangeably use either word. Kernel machines is a bit more general, and support vector machines is a bit more restricted. And like when we start talking about support vector machines, we're not going to use kernels for the beginning, but we're going to talk about kernels later today, and what they are capable of. So the cool thing about support vector machines, first and foremost, is kind of like we never have to do more than we need to, and again, as like in a couple of discussions before, we don't need to calculate the posterior probabilities. We can just identify decision boundary and decide like which class one data point falls into based off of that. And after training, in the end we receive a linear model, which is basically based on a weight vector, and the input that is then received in the network or in the support vector machine to produce a decision. And we don't have to look at all of the training data. We only have to look at like the reduced number of items in our training data, and this subset of items in our training data is called the support vectors. So like in contrast again to, for example, nearest neighbor methods, you have to look at all the data points. In decision trees, you walk down the trees and you have to walk through all the decisions, but also based off of subsets. But here you basically just compute a weighted sum with respect to your trained weight vectors and the identified support vectors, and you basically know which side you're going to fall on, and then you make a classification based off of that. Another important aspect, and we're going to talk about these support vectors in more detail in a second. Another important aspect is that there is one analytic solution, and there is no getting stuck in local minima. So that's kind of a cool feature as well. And one of the main ideas here is that support vector machines are really great in that sense that you're allowed to basically just get a good starting sense of like how good a classifier would be. And for example, if you don't have too large of a data set, you can compute the outcome very quickly, like within fractions of a second sometimes. I guess you have tried that in your homework, which is due soon, I think. And if you like run the different hyperparameters, it should go very quickly. Unless, and you can try that actually, if you want to take a much larger data set. So let's say you increase your data size tenfold or 20-fold or so, like 100-fold even, and you have, let's say, I don't know, like 100,000 data points in your data set, then the training of a support vector machine will be very, very slow. Like it might not even end in some cases. So it is a good thing that there is an analytic solution, but it's also like sometimes a bad thing that the computation might take quite a while. I'm going to talk about like a couple of differences here. So for example, in the standard support vector machines, your computational expenses are based off of the number of dimensions your data input has. So if you have a very high dimensional input, it might take very long for you to calculate the support vectors and to calculate the support vector machine in that sense. But through a trick, we're going to show that we can transform this problem from a dimensional optimization problem to a number of observations optimization problem. So like the number of training samples is going to be the bottleneck, and that's going to be a problem later on. And it's not just this transformation from like a dimensional optimization problem to a observation-based optimization problem, but also the fact that we transform the data into a high dimensional space that is kind of like easier to handle in some cases, and we're going to talk about this in more detail. All right, and lastly, which is actually kind of cool as well, is that the number of support vectors gives us an estimate of the generalization error. And I'd like to motivate this through a picture here. So, so do you think with, let's say, these three support vectors, which are here circled, so we have one in the plus category and two in the dot category, do you think we're going to make a lot of mistakes based off of these? Like this support vector machine is kind of defined by these three support vectors, but it's decision boundary here. And the question kind of is like, do you think that this is going to be a very hard problem? Like we only need 3 data points to like set up this separation. What would happen if we had like, I don't know, a ton more data points here, a lot of more data points here? So what I'm trying to get at is kind of like if the support vector machine is only defined by, let's say, 3 data points, that is an indication of there might not be too much, it might not be too complicated to separate these two classes. So if I had like 1,000 data points and I only needed 4 data points to separate those two classes, and remember there's an analytic solution that is perfect, like it doesn't make a mistake on the training set, then I would say that problem is really easy, right? But if I needed, let's say, 300 out of those 1,000 data points to be my support vectors, that means this problem is quite complicated, and I have like basically I have to like snake through my data in a very complicated way so that I can separate those two data sets or those two classes perfectly. Okay, so that's kind of like an idea there, but we'll have that in more detail in a second. So what is important here is that these 3 observations here are our support vectors. We have our decision boundary, so which is this like full black line here that basically defines if a data point that is new and unseen lands on one side of the boundary, it's a plus, and if it lands on the other side, it's a dot. Okay. The dashed line here is the margin. We had talked about this already, and this margin basically defines the space between the decision boundary and the location of the next nearest data points. Okay. In this case, we are trying to fit a linear line, so we try to like find a hyperplane in this 2-dimensional space. We find a line that separates those two classes. We'll see that we can make this more complicated. We can come up with like curves like that go around like this and like this. We can come up with maybe like a polynomial separation and so on. We'll talk about that. And these kind of like decisions on like if I choose a linear separation or a polynomial separation, a radial basis function separation, this is my decision of like what kernel I use. Okay, and we're gonna get to that point. So these are gonna be our kernels. Alright, so the support vector machine or the support vectors define the model and the decision boundary. And we talked about this before. If I take out any of these data points that are circled here, my decision boundary and my margins change. So they support this decision. Okay. If I remove any of these points that are not circled, nothing changes. So they don't support it. So that's important. The support vectors lie on the margin. You can see that they are actually on the margin, and removing them will change the model, and it will result in a different model. Removing any other points will affect in the same model as we have here. Okay, so that's important. And then that also basically gives us an idea. It's like, so if I wanted to find if a data point lands on this side or on this side of the decision boundary, I don't have to look at these points. I only have to look at these 3 points. Okay, so that's all I need to look at. Okay, so let's continue that. So the output of the support vector machine can be written as a sum of influences of support vectors, and these are given by the kernel function, which we'll discuss later today. So that, like, I only have to look at the support vectors. I don't have to look at all the data points. Okay, I kind of alluded to this. Kernels now will allow us to go beyond simple vector spaces, like beyond like linear separation or Euclidean distances. They can allow us to compute similarities in very high dimensional spaces very efficiently. So I can have like a 1,000,000 dimensional space, and I don't have to calculate the distance or the similarity of data points in that 1,000,000 dimensional space if I have a very smart and very like like a good predefined kernel. So for example, we can have kernels that measure distances between graphs or documents, for example. So what do I mean with like a million dimensional vector? So if you look at like the vocabulary of English words, there might be like 250,000, 300,000 words. If you want to include like I don't know, other languages as well, so that might increase and increase, right? But to measure the similarity between two documents, I don't need to look at if every single word in the English language happens in both documents or not. I just have to look at, in those two documents, which words coincide, right? I only have to count the, like 1,000 words here, 1,000 words here. Are these 1,000 words happening here or no, right? And I can just count how many are equal in both documents. I don't have to go through 1,000,000 different words, okay? So that's much faster as an example, okay?
If your data comes as a vector of million dimensions that is, let's say, one part for the word the, then you just have to literally search through, you still have to search through the whole thing to find if these two are matching.
Right, so if you calculate the similarity between two vectors, right, like one way to do that would be to compute the dot product, right? If you have 1,000,000 dimensions on that one, and then you have to have 1,000,000 dimensions on the other vector, and then you have to go through.
Yeah.
No, and it's like you have to do this 1,000,000 times. Yeah. That's slower than like going, like you have one document, you have another document, and he's like, okay, is this word here? And so you just basically, you can do that much quicker, I think, and you can also predefine, or you can define a new vocabulary based off of that document. You can check if those words are there and stuff like that. Yeah, and like the dot product between like a million dimensional vectors is not too complicated, but there are more complicated ones. And we're like, yeah. So the idea basically of a kernel is to allow you to quicker compute the dimension, like the similarity between two vectors. And I think it's most efficient, for example, if you compute radial basis function kernels, so where you have basically you just look at like how far away from the mean and the standard deviation this data point will be. Okay, and then yeah, we said that already. So like kernel-based algorithms are defined as convex optimization problems. There's a single optimum that we can solve analytically, and no gradient descent is required. However, and this is important, support vector machines, and we're going to talk about some of those parameters, are highly dependent on a number of free parameters, or like hyperparameters as we've called them before, that we need to define. So what are hyperparameters in support vector machines? The first one, and I think one of the most important ones, is the type of kernel. Like, do I believe my problem is linearly separable, or do I not believe that? And then we're going to talk about a few more, but if you, for example, choose a polynomial kernel, what is my hyperparameter there? Well, the order of the polynomials will be, for example, a hyperparameter. Do I think it's a quadratic problem? Do I think it's a cubic problem? So it like, and so that changes a lot as well. Another one is like, if I believe that I have a problem that's best solved with a radial basis function, well, then I need to define like what does it mean to have like a variance in that radial basis function. So the standard deviation parameter, so to say, in that exponent function, and we'll see that and the influence of that in a bit. Those will actually influence my machine as well. So that's important. And you know what to do here. Well, that was the homework, and you had that like the gamma parameters, and I think there was a C parameter. And I think C was the right one to choose. But no, I think Li Xing chose the wrong parameter. I didn't know like that there was like two. Anyways, so yeah, there are parameters that you have to validate for. Okay, and you probably have done that already. Okay, so all of these separations here for this problem here are valid solutions, and I'm just like trying to introduce, and I think we talked about this a little bit already, but we want to define what a optimal separating hyperplane is. And so we have all these solutions, and all these solutions are fine and really great, actually. Like, they separate the problem perfectly, no mistakes made. But why are these not optimal? And we kind of talked about this. And also, like, remember that these hyperplanes here are actually those that would be found by a perceptron or a neural network and so on, okay? They are the ones that they will find. They will not find the optimal one. So that's kind of like a big caveat here. So supportive machines are different from them. Alright, so why are they not optimal? Well, if I choose, for example, this one, and this is actually not the right observation, it would be actually here if I had a perfect sensor, or if I had some noise on my data, they would change a lot. So what I want to have is I want to have as much distance between my data points and the separation, so that we are not as prone to noise as like we are if they are actually touching. And like, what does it mean if we're prone to noise? Well, we might not generalize as well. Like, we want to have a good generalization with our optimal separation or separating hyperplane. That would go through here, square through the middle, so that the distance between this point and these 2 points will be maximum to the separation hyperplane. Okay, and yeah, so that therefore it might be good to find the one that is farthest away from all the training So how does this plane look like, and that is farthest away? The answer to that is like it has the maximum margin, and we define the margin basically as the sum between like this side and that side. So both of these together kind of like are the maximum margin. This is the hyperplane in the middle, and it goes right through the middle. So it's half and half. Okay, so there's and the important part is that there's only one optimal solution that maximizes the margin. Okay, and to visualize that, well, if it's this is my margin, I can fit it through here, I can fit that through here, I can fit that through here. But if my margin is this wide, I can't turn this around without like misclassifying that one, for example, or misclassifying that one or that one. Okay, so if the margin is maximally chosen, well then this one is rigid in the data and I can't wiggle it around anymore. Okay, so that's why there's only one solution for this problem. Okay, and it's just like a nice visualization of like how this is motivated. All right. So how do we get to this solution? This is kind of like, it's going to be a bit more complicated, a bit math heavy, but in the end, I think the main story or the main idea will be that we have a way to optimize for that using quadratic optimization algorithms, and at the very end of the lecture we're going to walk through one example where we actually do the optimization, and in the end we'll see it's not that hard. And the good thing, the really nice thing about this is you won't have to implement this by yourself probably ever, because there's so many like toolboxes and whatever out there that help you with this problem. So as usual, we have a training set with two classes. The training sample is defined as our like capital X. We have observations and we have class parameters plus and minus. So +1 is for class 1 and -1 is for class 2. We could change that to 0 if you wanted to, but since in the end the classification will be plus on one side and minus on the other side of the hyperplane, we just choose +1, -1, so we're not like restricting this at all. And now we would like to find a W and a W0 such that because that's how we want to classify it, like +1 and -1 on one side, so that that for class 1, this multiplication or like this dot product plus bias is greater or equal to 1, or smaller or less or equal to -1. Okay, and note that there is a +1 and a -1 here and not a 0, right? So it's not enough to say that we're on the right side of the thing, or on, like by just a little bit. We actually want to be on the right side +1, and this kind of like called, so to say that the hinge loss is similar to that. So hinge loss would be, for example, instead of just trying to be greater or less than 0 to be correct, you want to actually be greater or less than +1 or -1. So you want to be across a certain distance. Okay, so this whole thing now can be rewritten into this, because we can like bring in the R and change basically these signs there. Okay, so this can be rewritten as one function, and it's important that it's not enough to have this. Okay, so we want to be greater or equal to +1 with this. So, like just a quick kind of question, what would happen if this is, like if we have a data point, we do this multiplication, we're kind of done already, if it's equal to 1, what happens then? What is that, what type of vector is that? It's a support vector. It's on the hyperplane, like the margin of the hyperplane. Okay? And if it's greater 1, well, it lands somewhere out here. And if it's or here, depending on like the plus or the minus sign, okay, for the R. If it is in a classification problem, and we have learned this, what happens if it is greater than 0 but smaller than 1? It ends up somewhere between the hyperplane and the margin. Okay, so it's kind of like it's in between those, and that's fine for classification. We don't really need to enforce a margin on classification, but we're going to talk about like what happens if that is important during training as well. So, all right. And as I said, like this is required that we want the instances right on the not only on the right side of the hyperplane, but also a certain distance away. And this +1 allows us to compute this distance. And the distance from the hyperplane to the instances closest to either side is called the margin, which we want to maximize. So it's like the margin is going to be the part that we want to maximize, and then that will lead to the optimal separating hyperplane, which then only has one solution because we can't like move that around anymore. All right. Oops. Yeah. So if we want to calculate the distance of a point to a discriminant, well, we need to calculate these kind of formula. So in this case, we have the absolute value here, but we can also just reuse this R parameter again. And then we kind of normalize this with the weight vector, right? Because we want to kind of like have this, in a sense, normalized for all of our like weights. We don't want this to be independent of like the location of the separation hyperplane. And this normalization is kind of just like to keep us like in a certain boundary. So like this distance now should be at least a certain value, rho here, for example, and again, there are arbitrary many solutions for this when we maximize for rho. Like that's like we can have this super large or super small, and like we can wiggle that around. But when we scale this to W, for a unique solution, we fix basically this rho times the size of this vector is equal to 1. Okay, so we maximize the margin when we minimize this W. Okay, so like we want to have this vector to be as kind of like compact as possible. All right, so we maximize the margin when we minimize this. So that's kind of like the first step towards reformulating this problem. Geometrically, this all looks like this. So first of all, we have 2 times the margin, which is like 2 divided by this vector, or weight vector. Basically, that defines our margin. We have this bias that's also normalized with our weight vector. And then we have these distances that are also normalized with our weight vector. Okay, so that's kind of like it just to help us to bring this all into like one solution. And okay, so the task can now be defined as basically minimizing 1/2 W square, which is then like basically the square of the norm of the weight vector, and it's subject to again this constraint here that we had before, and we can formulate this as a quadratic optimization problem whose complexity depends on D, and the D is the dimensionality of our vector. So we need to find, well, the optimal W, right? And W is, as X is in the same dimensional space, so W exists as a vector within the same space as the input data itself. So we need to find D many parameters to solve this plus actually W0, okay? And if this, like, and we're going to talk about this a little bit later, but if this dimensionality grows very large, well, we have to find many of these parameters that fix this problem, okay? And so that will be a bit too costly, and we want to like reformulate this into a problem that's not dependent on the dimensionality, but dependent on the number of observations. Okay, so, and there will be instances that are 1 divided by the norm of W away from the hyperplane, and the margin will be 2 divided by norm of W wide, okay? And the points that are, well, 1 divided by the norm away, these are the points that are on the margin on either side. Okay, so these are our hyperparameter, these are our support vectors. Okay, and so this is what we want to solve, and we talked about this before. Often there is not a solution for this problem, because sometimes we will have like a square out here or a circle out here, and we wouldn't be able to find the solution to that problem. So like if we have only linear, if our algorithm can only find a linear separation, well, if the problem is not linearly separable, this will not help us. What could we do in that sense? Well, one way to solve this, and we're going to see this in like a simple visualization for a couple of examples later. But one way to solve this is if you have like a number of data points, and you, instead of like represent them in like a two-dimensional space, you represent them in a very high-dimensional space, it is much more likely to find a linear separation between this small and limited number of data points. So one way to do this is to basically have many more dimensions than the original space. However, as we said, we will need to optimize this, this optimization becomes much more complicated because it depends on the dimensionality D. Okay, and so what we need to do is to rewrite this problem so that it's rather dependent on the number of observations n rather than the dimensionality. Okay, and that's kind of like what we're going to do now. So we have to kind of come up with a solution that's not dependent on the dimensions but on the data points, and that could be good or bad either way. If we have many data points and the problem is really complicated and we don't have a sufficiently expressive kernel, we might run into trouble again and like might have to optimize for a long time. Alright, so the way to do this basically is to introduce our Lagrange multipliers, which are basically just these alpha parameters, and we have an alpha parameter for all of our data points. So we go from basically t equals 1, so like observation 1 to observation n, and we have these multipliers here, and then we brought in our constraint. So this is the r plus or minus depending on the x, which is in our data set. Then we have these weight vectors again, we have the bias again, and then we brought in this like greater or equal 1 as a -1 into this equation, and we have still our optimization problem, which was to minimize this problem here, okay? we can multiply that out, and now we basically bring the alpha out to this guy and have two sums, and we now optimize this by minimizing with respect to w and w0 and maximizing with respect to alpha greater or equal 0. So these are our Lagrange multipliers. The optimum will be a saddle point here in the middle where we have an optimal solution in all directions. So, and the cool thing about this again will be kind of like, okay, so we need to optimize for w's and w0s, and like if we set to 0, like a lot of these terms will fall away. Okay, so that's kind of the idea when we write this that way. So to maximize this with respect to alpha, we and subject to the constraint that the gradient with respect to w and w0 are 0, which we had before in our in the gradient descent. So we always set to 0 and take the partial derivative and see in which direction we have to go. And here we set it to 0, and what we find is that with respect to w, we get that w equals to this sum here, and w0 we get that this multiplication basically should add up to 0. Okay, so if we multiply this out, the norm is basically the dot product. The norm squared is the dot product minus w times this part. This is w transpose. This is that sum up here, so that's w. So that's w transpose times w, which means it's the dot product again, minus w0 times this. Well, that's 0, so that's going to fall away. And then we have the sum over alphas. So half dot product minus dot product is minus half dot product, and then we can basically replace those w's with these, and since we have one transpose here, we need to basically do a double sum. So we have in one case the s as an iterator over all the data points. In the other case, we have t as the iterator over the entire data set. So we have n here, and n here. Okay? And then here we compute the dot product between the two data points, and in this case kind of computes the similarity between them. All right. So so this can be solved with using quadratic optimization methods, and the size of the dual now depends only on n and not on d. Okay, because here we only have to iterate over n's, and these alphas that we need to find are also there are only n many of these alphas that we have to find. So if we solve for alpha t, we see that there are n many parameters. I just said that, and only a few of them. This is the good thing. Only a few of them are not equal to 0. So most of these alphas will be 0, and that means that all of these things here will just be 0 most of the time. So we don't have that many parameters. In fact, for all of the xt's where alpha is greater than 0, they are actually defining this hyperplane, because that's kind of otherwise they have 0 influence on the optimization. So they are actually our support vectors. So these xt's are our support vectors. And yeah, we see that basically down here that only the alphas that are not equal to 0 will have influence on this w. Okay. And so the support vectors basically satisfy exactly equals to 1. So this term equals 1, and they lie on the margin. And from this term here, we can get the w0 from any one of those. So we can reformulate this basically bring this part over on the other side and see that basically W0 can be computed from any one of them. And the discriminant now basically can be found with W and W0, and this is called the support vector machine. It's basically this formula with our W's defined as a alpha times our input vectors. So this is kind of like the responsibilities for each of the data points with respect to the hyperplane. So if this is 0, this x doesn't have any influence. So these are all these points out here, and if it's not 0, well, then it's exactly these points here that are on the margin, so they have an influence on the weight vector. And for this point, the hyperplane, like the value is greater than 1, and so on. Okay. So our during testing, we just have to decide if this value is greater or less than 0. And decide then on which side of the hyperplane this value falls, and like that gives us the class. All right. So this is kind of like what the outcome will be. And again, we're going to do one of these optimizations with a simple problem, but in the end, it's not too difficult. Like you have to just come up with many linear equations and try to find the optimal alpha values. Okay, so I'd like to now introduce a little bit of a different problem. So here now we have a non-linearly separable problem where now we have these two additional data points here that are in one case on the wrong side of the hyperplane, right? So D is on the wrong side of the hyperplane, and in this case C, this data point is actually within the margin, which is not allowed, right? So like that would be not a valid solution based off of the previous computation that we had. And this is also not valid as a solution because obviously it's on the wrong side. So one way to deal with those things that are happening here is to introduce a new variable, which is called, in this case, a slack variable, which is xi and or chi, I don't know. In this case, for example, if it's out there, which is on the right side, outside the margin, not on the separation hyperplane, or like not on the margin, well, here we don't have to count any slack, so we can compute this as 0. For this guy, what would that be? Or for these guys? Do we have to count slack or no? Do they violate the previous restrictions that we had? They don't. So like we would say all of these support vectors here get 0, right? While these now become also support vectors, but they are violating these constraints, we have to like give them some penalty. We don't really want them, but we can deal with them. So what would this guy get? Well, this guy will get a slack variable that is greater than 0. But it's on the right margin, or on the right side of the margin, so like it's greater than 0, so this value is not going to be 1, but it's like 0.2 or like 0.3. So this, like for this guy, it's going to be greater than 0, but less than 1. Okay. And for the C parameter, and for this guy, well, this one has turned, or like it has changed the sign, right? So So it is on the wrong side. So this psi value here needs to be greater than 0 again, but also greater than 1, right? So it's greater than 1, and depending on like how far this is out there, it will be growing. Okay, so this is not bound by anything. So it could be infinity if like it's over there somewhere. Okay, so that that is a problem, and in our optimization now we want to introduce these slack variables. So we want to allow the model to have some slack and like allow these parameters, these values to be within the margin or on the wrong side of the separation hyperplane, but not too much. And one way to do this, and one way to introduce a lot of like these kinds of constraints onto machine learning problems is called regularization. So one of the things, for example, if I want to like have my weight vectors or my activations in a neural network to be small, I would always introduce like into my optimization problem like a value that reduces that. Like it wants the values to be as small as possible. For example, the L1 norm or L2 norm on weight vectors would be introduced, or like that keeps all the values of the weights as small as possible. Or you want to have activations to be very sparse, you only want to have some outputs and not many, and so on. So there's many ways to introduce this kind of stuff. And what we do is, well, basically, we want to compute this kind of soft error, which is the sum of all the xi's. And we want to keep this as small as possible. So we just introduce this into our optimization, which we need to minimize this, right? Before, we just minimized this, but now we minimize this plus this guy, okay? And, well, it's the soft error, and if c equals 1, well, it's only the soft error, but we can actually manipulate that c parameter. So that's another hyperparameter of our optimization. So we can turn this up to infinity, and that would mean we do not allow any slack variables. Okay, we need to find an optimal solution. If we turn this down to like very tiny, well, you can have so much slack as you want, right? So this is a tuning parameter. Like you have to tune this parameter up and down and try to find the right value for your problem. And so this kind of like softens up this optimization, and you're allowed to kind of like tune this amount of slack. And again, like this, we have these. And so C is a penalty factor and should be validated using cross-validation strategies, like any other model parameter that we talked about before. So these are like, this is kind of like a regularization term here. Okay. And so in the unconstrained form, we can now add this new penalty term, basically just adding this guy here, and then we add some size here because we had it over there, and then we also have to multiply it out with our r's. So we basically end up with this equation there. And again, we have to derive that for w, set it to 0, and again we get the w is equal to the same thing as we had before, and w0, same thing, and with respect to these parameters, we get now this thing here, which should add up to 0, and well, basically what that does to us is this formula in the end looks exactly the same as before. There's no difference between this dual form and the previous dual form. The only difference is that we have these alpha values now subject to different constraints. So the C parameter comes up in this additional term there. Okay? So that's the only difference.
So how do we understand the new constraint? Why is
Why does C?
Yeah.
because that's a good question actually. So that is a very good question. So let me think. Well, that basically means that if we do not allow, so if we heavily weigh these variables that violate our constraints, okay? So like when our data points violate the constraints that we had before, like these D and the C parameter, then we need to punish that a lot, okay? So theoretically, we can allow them to go on the wrong side of the margin, or into the margin, or on the wrong side of the separation hyperplane. But to make this work, we will have these alpha values to be like really large, right? So, but they have to be within this range. So if this C value is large, we can optimize this very easily and like basically just tune up one or two of these values to be very large, or like several or many of these values to be very large. But if we do not allow this to be a very large value, we don't allow them to go on the wrong side. So this just constrains our optimization here. There is the influence of these of a certain points is restricted through the C. So if the C is very large, we can come up with a very complex combination of our of the input vectors, and basically allow them to be on any side of the margin or of the hyperplane. So it just restricts our optimization here.
But like after taking account like the error, the slack variable, like
yeah.
For sure like this alpha value will change, right? But he just like here like the constraint just like the boundary becomes larger, so it has more flexibility to change.
Yes. Yeah. Yeah. Okay. And so the support vectors again are the ones that are alpha greater than 0, but it's including those guys. And so if they are restricted, I think that these so the ones in the margin or that are misclassified have alpha equals to C. And so if we have that C value too large, well, that basically has very easy solutions to that. And those like most of them, or the good support vectors have the alpha value that is smaller than C. Yeah. And can be used to calculate W0. So all of these we can't use to calculate W0. Yeah. And so this is just a repetition of what I mentioned before. Is like support vectors that fall within the margin are hard to classify, and so if they weren't present in the training, and in fact the number, so if this guy wasn't present in the training data, or this guy wasn't present in the training data, it would be actually really difficult to classify those, because this guy is really close to the decision boundary. It might be a dot, it might just be on the other side. So this is what I mentioned before. It's kind of like an approximation of the expected error on new data is based off of the number of support vectors that are needed for the model, like normalized by the number of observations. So if I have a very large problem, I can have many support vectors in there, but if I have a very small problem and I still need many support vectors, that might be an indication of like how difficult that problem actually is. Okay. And then this is what I mentioned earlier. Basically, using slack variables within our SVM, we imply that we make an error on both instances, both when the instance X is on the wrong side as well of the hyperplane, as well as when their margin is less than 1. So basically, what we're doing is we use this hinge loss, where the loss is non-zero for the values all the way up to 1. So if we are on the wrong side of the hyperplane, we have an error like this, so like pretty large arrows here. So like we can have that go up to infinity. But if we're on the right side of the hyperplane, we still make a little bit of an error, but only when we reach the margin, and beyond we don't make an error. So that's kind of like a difference there. In contrast to like 0-1 loss that we had with like perceptrons or neural networks, if we make if we have the wrong sign, we make exactly 1 error, and if we have the right sign, we make 0 error all the time. And then like these are the different ones, like squared error or like cross entropy, that are similar to hinge loss, for example. It kind of like hinge loss is easier to compute and it's more efficient. And then the hinge loss is kind of like defined as such, but you can see it visualized there pretty easily. Okay, so we can leave it at that for the moment and like do maybe like a 5-minute break and come back at like 11:05 to discuss the kernels, and we're going to start with Cover's theorem.